Hello, everybody, and welcome to today's MIRACUM-DIFUTURE seminar series. I would like to welcome very much Ilya Mazein. He is from the young researcher group MeDaX at the University of Medicine in Greifswald. And in today's presentation, we will illustrate us the MeDaX pipeline, a way to transfer clinical data, FHIR data into a knowledge graph. Thank you for joining us, and we are eager to hear your presentation, Ilya.
Thank you very much. So, hello, everyone. Yes, my name is Ilya Mazein, and today I'm going to be telling everyone a little bit about clinical data and knowledge graphs, and sort of presenting the latest tool that we have developed called the MeDaX pipeline. So, to tell a little bit about where this is all happening. So I am a researcher at the Biomedical Data Exploration Junior Group, MeDaX for short, where the name comes from. And we are a part of the Medical Informatics Laboratory at the University of Medicine, Greifswald. Okay, let's jump into it. So where this all started. So as I'm sure everyone here knows, the FHIR format is currently the standard for storing and exchanging clinical patient data, especially within the structure of the MII. While it is a great format for storing the data and exchanging it quickly, it is not very convenient for data exploration or data analysis. Essentially, it describes different clinical entities through a number of features, as you can see an example here. And on the right, at the very right box, you can see how this file actually looks sort of in its raw state. Basically, they are flat text files encoded in JSON, basically sort of a number of nested dictionaries and lists and key value pairs that describe the different clinical entities, and their features. And so in its raw state, it looks a bit scary for analysis, not very convenient. And so the thought that started this was, how can we make clinical data more easily accessible and explorable both by clinicians and researchers? And that's when we thought of graph databases. Now, I'm sure we're all familiar with graph databases in one way or another. For example, they are surely in our everyday lives in things such as social networks, but they are becoming increasingly popular within the bioinformatics community as well as biomedicine, mostly due to their ability to sort of intuitively represent network data. And as most data in medicine and biology is quite heterogeneous and highly interconnected, such as protein-protein interactions or metabolism regulation and many others, more and more they are beginning to be incorporated into a graph database form. Now, just to quickly say, graph databases are basically a number of nodes which represent the different entities stored within the database with various properties or key value pairs describing them, while the edges of the graph represent the different connections between those entities. Now, graph databases are also great not only because they are well suited for data like network data representation, but also because they possess a number of intrinsic features that are useful for querying and analyzing data, such as graph traversal algorithms or such data analysis algorithms as clustering, pathfinding, and so on and so forth. And yes, so the thought behind this was, what if we could represent clinical FHIR data in this graph format? Now, how do we actually do it? Well, the first step of our pipeline is a script that basically parses the different FHIR bundles and sort of recursively goes through the tree-like structure of this JSON, all of the nested dictionaries, and generically, basically, transcribes all of the data stored within the JSON in a similar structure to the JSON, but into a graph. So as you can see here, all the different color-coded sections of the nested lists and dictionaries and how they correspond to their respective nodes in the resulting network X graph. Now, there are around 157 different FHIR resource types, and of course, creating a custom conversion script for each and every one of those resources would be quite challenging, which is why we go for this type of generic conversion, so that no matter what kind of FHIR resources are presented, my apologies, are presented to the script, it can easily transcribe them into a graph form. But because we do this in such a generic way, and sort of follow the inherent internal structure of these raw JSON files, we often get quite large graphs, especially if we're dealing with patient bundles, meaning the patient resource at the center and all of the other different clinical entities connected to it, such as observations, medications, hospitals, practitioners, and so on and so forth. The graphs are quite large. And so we had to think of ways to sort of optimize our graph storage and our graph structure to make it more accessible, more concise, more accommodating. And we have two main strategies for that, which are implemented in our pipeline, both to do with the way things are structured. So the first one would be to do with, now, references are the way that different FHIR resources are connected to each other. So for example, an encounter has a patient that is one of the participants of that medical encounter. And in the original structure of the JSON file, there would be a nested dictionary containing the reference, which points to the identifier of the patient in this case. And so when we generically transform from the JSON file into the graph, because of this nested dictionary, we get a subject node, which contains the reference of the patient that is the subject in this encounter. But seeing as we now have a graph, we can connect the encounter and the patient directly without the need for this sort of intermediate step. And so we find all the nodes containing references, and using those references, we directly connect the necessary entities while keeping the information about the type of connection. So this was a subject node with the reference in it, and now we have a direct reference connection, keeping in mind that the type of the connection is subject. Now, the second strategy for optimization we had was to do with features of the different resources. So again, in the original JSON file, due to the nature of how it is structured, nested dictionaries, lists, value pairs, and so on, the features describing a certain resource are not always simply structured. It's not always just one key value pair, for example. It can have a number of layers to it. And so when generically transformed into a graph form, you can see here in this example that different features of the patient at the center here can be represented as pathways. They can be of various lengths, they can branch, And yeah, this complicates the structure of the graph. However, since all of these different paths each describe a singular feature, what we have attempted to do is shrink these paths, or convolute them, if you will, into singular nodes that are all connected to the resource that they are describing. So all of the information contained in the different nodes of this path is condensed into a singular node, making the graph structure more simple while preserving the information stored in this path in this one node for easier accessibility. And so when we apply both of these optimization tactics, here in this example, this is the same graph. So just after the generic conversion, and then here it is again, after we have applied both of these optimization tactics. Now you can see here on the right that the nodes are a little larger than here, just for a reference of scale. So actually, this graph on the right would be even smaller, but to show it here, yeah, just to see the structure a little bit better, it's a little larger. But anyway, you can see that the structure is much more simple. There are a lot less nodes, and you can see all the connections much more clearly. Now, after we have optimized the structure of the graph, we then integrate it with bioCipher, which is basically a framework tailored to biomedical knowledge graph creation. And it allows us to do such things as ontology integration. We're currently using the default bioCipher ontology called biolink, which gives us another layer of organization and structure to our data. And ultimately, it also eases future integration of other diverse data sources through ontological connections. Now, we have recently started to test and integrate our MeDaX pipeline at our local data integration center at University of Medicine Greifswald. And while doing it, we came upon a number of challenges, which I'm going to quickly go through now to see how these things happen in a real world sort of testing environment. So the first thing we came across when working with the DITS server was that obviously the DITS has stored in it a large number of patients. And the first thing we came across when trying to process large numbers of patients was that I think it was around about at the 1,000 patient mark that we ran into a random access memory shortage. And so we had to think of a way to circumvent that and to allow ourselves to process these large quantities of data. And so the solution that we came with is a batching approach, meaning that a certain part of our pipeline deals with a fixed number of patient bundles at a time. I think it is currently, the batch size is around 250. So what happens is each batch gets taken from the server. It is converted to the graph as previously described. It is also optimized, and then we get the whole graph for these 250 odd patients. And we export all of the lists of nodes and edges from this graph and save it, and then go on to the next batch and process that, save the nodes and edges, and so on until we have processed everything that we need. And then all of these nodes and edges are entered into bioCipher, and then the enrichment takes place for the whole graph itself. Now, this was a nice approach to get around the memory shortage. However, in the process, we ran into two more complications. The first being that there can be duplicate resources in different bundles. So imagine you have a number of patients that all belong to the same hospital. And in each of these patient bundles, you would get a hospital resource that represents the hospital where this patient comes from. And as they all come from the same hospital, this would obviously create duplicate resources and ultimately duplicate nodes in the graph, which we would not want. Now, the solution that we came up with for this was to implement a new unique ID for every resource, which has a structure of resource type plus the resource ID. And in the end, once all of these batches have been processed and are imported into the final graph database in Neo4j, these unique IDs are filtered, making sure that only one unique instance of every resource is kept and no duplicates are found anymore. Now, the second challenge coming from the batching approach is that obviously the references that we create directly between the different resources, that happens in the graph processing step. And the graph processing step is separate for every batch of patient bundles, meaning that certain references or connections between resources that are potentially located in different bundles would be missed. And obviously, we would not want to have any missing data. And so the solution to address this challenge was that if we find a reference at any point that doesn't find the target that it is looking for, a dummy node is created instead that represents the target. And this dummy node contains the corresponding unique ID, which is again the resource type plus resource ID. And in the final step of the pipeline, when the Neo4j import happens and we create the final graph, again, we have a filtering of duplicates, and we make sure to remove all the dummy duplicates and leave only the one instance of the actual target node itself. And since the references point to the corresponding unique ID, which was the same in the dummy nodes and the actual original target, in the end, the references all point to the right resource. Now, some perspectives for future work that we currently have for our pipeline is, as I mentioned earlier, integration of more diverse data sources, such as the NARF graph, which is the Novel Analysis and Recommendation Approach for Study Features, which contains a number of metadata describing different studies, which would be useful in both in selecting a study based on your own criteria, or even finding patients with the needed also corresponding criteria for a specific study. And we are also excited to test some integration of semantically enriched tabular data, for example, such as immunology data, which is stored in table form, but could potentially also be transformed into a graph through sort of additional adapters that could also be integrated into BioCipher and ultimately create a multi-layer graph connected to different ontological instances, which would be useful to query for all the different applications that you could think of. And so to recap, the MeDaX pipeline, it is currently available in its first stable release. You can check the URL at the bottom there. And what we do is we take clinical data, transform it into a graph, optimize that graph, ontologically enrich it, and create a graph database containing the new knowledge graph created from the original clinical data. I would like also to thank all the great teams that have supported us in developing this tool at the DITS of the University of Medicine Greifswald, as well as our own medical informatics laboratory, and of course the bioCipher team. Also, here are some useful references for things that I have referenced during this presentation. And yeah, thank you so much for your attention.
Thank you very much, Ilya, for the very nice presentation and illustrating us all the hurdles you had to manage during the complete process developing this pipeline and how you managed to overcome the problems. Is there any question from the audience? I don't see any question yet. I have a question. You told in terms of the optimization, the memory problem, and
Yes.
you told us that reaching a number of about 1,000 patients, you got into the memory problems, and you then put it in different batch packages of size of 250. So I assume that the whole DITS Firestore has hundreds of thousands of patient records. For what real size have you finally ended up to pursue this transformation? And what was the time to run the pipeline then to complete it finally?
That is a good question. Actually, we are currently working on running the whole pipeline for the whole amount of data in the data integration center. And while I cannot currently definitively confirm, I think the latest that I've heard from a member of our team that is actually running the pipeline, that it has successfully run on the whole amount of the DITS data. I'm unfortunately not sure the exact amount of time that went into that. But I think that it was less than we originally thought it would be.
Okay, I see a hand of Judith. Maybe Judith can add something about this.
Yeah, thank you, Ilya, for the talk and for providing the information to the people. Yes, I also don't know exactly how many hours it ran, but actually we had in the first, so we, as you said, it's about 100,000 patients. And we had first thought that we will, in the current setup, then need maybe even a week, but it ran through very fast. So I think it was below 3 days. And it was able to build a full graph out of all the 100,000 patients. So this dispatching is just an intermediate step, and at the end we put everything together in one graph, and that works and can also run at the DITS. So the memory shortage came from this network X structure that was built off, because using this package, it tried to hold the complete nodes and all the properties of each node and every edge inside the memory, while building the huge graph of all the 100,000 nodes and edges. And
okay, thanks. Yeah, I had one more point where I think I didn't completely understand the optimization process. You mentioned that sometimes you had very long passes to define a complete feature, and that you decided exactly to shorten the passes so that you map every feature directly to the patient. So as in this image here, I would imagine then that you have only always only passes going from the patient, and the length of the pass is only one step to come to the next node, and then everything is finished. Is this correct?
So you mean after this optimization step?
After this optimization step, yes.
Yes. So the way that the graph would be structured is that every resource would have a number of feature nodes one step away from it, as well as the different reference connections between all the different resources.
So maybe I misunderstand the image here. So because here in the right you illustrate that you have the patient so that every feature is just directly in another resource. So I assume all the gray circles are resources.
Oh no, sorry, my mistake. So the gray nodes illustrate different features of this resource.
Okay. But is this just one resource then, which you mentioned here? Or
yes.
Okay. So for different resources, how would this then be illustrated? Is it still just adding new nodes to the patient? Node connections to the patient? Or do you still have then longer nodes? Because in the next image, if you just go to the next slide, there at the right, it looks as if there are still some longer nodes. They are shorter than at the left, but there are still some longer pathways.
So it might look that way, but actually, I don't know if I can zoom in here. No, I don't think I can. But if you can try to see all of the orange nodes in this graph represent different resources, and all of the gray nodes represent different features, and all of the features are definitely one sort of one step away from their corresponding resource, and the red connections represent references between the different resources. So I'm not sure. It might look a bit. It might be a bit difficult to see in this example here, unfortunately. But every resource in this graph would have this kind of structure to it. Yes.
Okay, now I understand. So the final question is, at the end now, you have everything in a Neo.j graph database.
Yes.
The question is, what for? What are you doing with this graph now? Do you have any further usage? Typically, what we have in our FHIR stores, we transfer it to any new format in order to do some statistical analysis or evaluations or some filtering of the data. Have you done this for any purpose on the graph database then? And have you compared it to the same querying on the original FHIR data? Is there an advantage, a better benchmarking for graph database then? Or what is the final purpose of transferring it into the graph database?
This is a very good question. So as I've described earlier, graph databases have a number of features that while we haven't benchmarked them specifically for this task at hand here, as we only recently got access to the DITS data, and we're currently only now, as you've heard, running it through the whole thing. So we don't currently have any practical test benchmarking to do with this data specifically. That is to come in the future. However, it has been found in many different other studies that graph databases have a number of features that make them much more effective than your traditional, more relational-based strategies. But yeah, we're currently looking and working together with members of the DITS to evaluate the database in the DITS environment, and as well, we're currently looking into medical and clinical use cases, which we hope to share in the near future.
So we are very eager to hear of some advantages as soon as you have done some evaluations and analysis of the final graph data and applied it into any use cases. Judith, I saw your hand. Is it all right? Okay. Or
yeah, no, Ilya now mentioned also that we are going to do that. So like the real problem was really to transfer the theoretical development like that we did with the synthetic data into the DITS environment. And now that we have that, we hope that we can come along with a lot of actually useful applications for it. We also think that it's a nice feature, for example, to train machine learning models on the graph and see what they can do with it.
It'll be exciting to see how you do it and what the results will be. So a lot of follow-up information to look at. So we are looking forward to seeing you in a follow-up seminar.
Great.
Is there any more questions from the audience? Looks like no more open questions. So thanks a lot for coming to give your presentation about the MeDaX pipeline, Ilya. And to all in the seminar, I wish a nice and successful week. See you next time. Bye.
Bye.